Our second chapter in chapter 6 is from section 6.3, and that's the logistics equation. Okay, so logistics equation is a differential equation used to model population growth. So generally when we talk about population growth, we say that it can be modeled using an exponential function. But sometimes there's instances where a natural condition or some type of restriction would limit the population. So the logistics equation would be a more realistic model for the growth. So logistics is a differential equation. This is what it'll be defined as always. K represents our growth constant. A is our carrying capacity. Okay, that represents the limit on whatever population we're looking at. And then, of course, when you'll look at what the solution is, but we'll have some initial population. With any differential equation, the graphical solution is the slope field. Okay. The slope field, notice that there's two horizontal asymptotes. Okay. There'll be a horizontal asymptote at A, your carrying capacity, and then there's a horizontal asymptote on the x-axis at y is equal to 0. Now, it doesn't make sense for our population to be negative, so we will pretty much disregard the slope field in the fourth quadrant. If our population is decreasing, okay, then as time continues, this should be a t, not an x. As time approaches infinity, then eventually we're going to reach our carrying capacity, this value a. So your population, if your population is greater than your carrying capacity, then eventually your population will decrease and it'll reach that capacity A. If your population is increasing, then we're saying your population would start less than your carrying capacity. So notice your population will increase, but it'll still eventually level off at whatever the limit is. Okay, so two horizontal asymptotes. Y is equal to 0 and y is equal to A. The point of inflection will occur at A over 2, so your carrying capacity divided by 2, halfway between the asymptotes. At the point of inflection, your rate of growth is a maximum. So your population grows quickly, and then it'll slow down, eventually reaching its limit. All right, the analytical solution. This is where we would do our separation of variables, collect the y's, and we collect the x's. Okay, we know k is a growth constant, so we'll just leave that on the side of x, and we go through our calculus techniques. Now we'll do this together in class because it's pretty involved, but we'll show tomorrow that this is what the analytical solution is always given a logistics differential equation. So for the examples today, we're going to use that. B, okay, there's a couple different ways we can find B. One way, notice what this value represents. It's the difference between the initial population and the carrying capacity divided by the initial population. Okay, so solve dy dx equals, given this differential equation, with y of 0 is equal to 1. Okay, so the logistics differential looks like dy dx equals divided by a. Okay, so the given differential sort of looks like a logistics differential equation, but we're going to have to do a little algebra to fit it into this exact form. So if I look in my parentheses, I need that first value to be 1. So let's factor out of 4 times 4. If I divide each term by 4, I'm left with 1 minus y divided by 4. Okay, multiplying these. 1.2y times 1 minus y over 4. Okay, so now look at the parts that I have. K is equal to 1.2. A is equal to 4. So then just simply plugging it into my solution y equals A all divided by 1 plus BE to the negative K times T. So y equals, my carrying capacity is 4. My value for K is negative 1.2, or is 1.2, excuse me. In the equation, it's negative 1.2. Now let's think of finding that value for B. That's where this can come into play. So I know my y of 0, if I replace T with 0, that's equal to 1. Okay, so I know e to the 0 is 1. So that gives me my value of B to be 3. So putting all the pieces together, my solution, the solution to this logistics differential equation, y is equal to 4 divided by 1 plus 3 e to the negative 1.2 t. You need to be able to recognize logistics differential and what its solution is. Again, when we do the solution in class, you'll know why you want to commit this to memory. Okay, next example, and this is the second and last one we're doing. Take a minute, copy this down. 10,000 acre forest has a carrying capacity of 1,000 deer. Assume that the deer population grows logistically with the given growth factor. Find the deer population if the initial population is 100. Okay, so population, that's the solution to the logistic differential. So I know my carrying capacity is 1,000. We're given the value of K to be 0.4. And tomorrow in class, we'll do examples of where you have to determine the value of K. Now, on the first slide, when I gave you the solution, another way to solve for B, carrying capacity minus initial condition, divided by initial condition. So it's really 6 of one, half dozen of another. Okay, 900 divided by 100, this gives me B is equal to 9. If we plug that information in, okay, so replacing T with 0, and I set this equal to 100, it's just a matter of, do you want to have to remember another formula for B, or do you always just plug in the initial condition? So dividing by 100 gives me 100 equals 1 plus B. I get the exact same value for B. Oh, no, I don't. Okay, I'm an idiot. 1,000 divided by 100 is 10. 10 minus 1 is 9. So I'm lazy and I don't want to redo the whole video. But now I get the same value for B. All right, so the deer population, if we want to make variables the same, carrying capacity is 1,000. 1 plus 9e, and then we'll plug in our value of K. So now we're going to use this model for the next part. So same information, but now find the time t when the population is equal to 500. So we just found a model for the population, and that's 1,000 divided by 1 plus 9e. Okay, so find the time t when the population is equal to 500. So replacing P of t with 500. All right, so your homework this evening, solve this equation for t. okay, and we'll say approximate it to the nearest tenth of an hour.